Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial topic in physics, circular motion. By the end of this tutorial, you will be able to solve problems involving angular velocity, angular acceleration, angular displacement, and the number of revolutions. We'll be working step by step through several examples. First, a very important note. Throughout all these problems, we are instructed to use the value of pi as 3.142. Make sure you use this specific value for your calculations to match the provided solutions. Before we begin, let's quickly review the key formulas we'll be using. These are the building blocks of circular motion. First, angular velocity, represented by the Greek letter omega, is equal to 2 pi times the rotational frequency, n. This formula connects the rate of rotation to its angular speed in radians per second. Next, angular acceleration, x, is calculated by dividing the change in angular velocity by the time taken. It tells us how quickly the angular velocity is changing. Third, we have average angular velocity, which is simply the sum of the initial and final angular velocities divided by 2. This is used when the acceleration is uniform. Fourth is angular displacement, theta. It's found by multiplying the average angular velocity by the time. This gives us the total angle rotated. And finally, to find the number of revolutions, n, we can divide the total angular displacement in radians by 2 pi. Alternatively, if we know the average rotational frequency in revolutions per second, we can multiply that by time. Knowing these 5 formulas is the key to mastering these problems. Let's start with our first activity. We're beginning with activity 2.1, question 1. Here's the question. A flywheel rotates at 12 revolutions per second. If the radius of the wheel is 0.4 meters, calculate A, the angular velocity, and B, the angular displacement after 0.2 seconds. Let's start by identifying the information given in the problem. We are given the rotational frequency, n, which is 12 revolutions per second. We are also given the radius of the flywheel, r, as 0.4 meters. Now let's solve part A, finding the angular velocity. Our goal is to find omega. We use the fundamental formula connecting angular velocity and rotational frequency. The formula is omega equals 2 pi n. Now we substitute the value for n and for pi, as per our instructions. Substituting, we get omega equals 2 times 3.142 times 12. Performing the multiplication, we find that omega is 75.408. The units for angular velocity are radians per second. So, the angular velocity is 75.408 radians per second. This tells us the rate of rotation in standard units. Great, part A is complete. Let's move to part B, finding the angular displacement. We need to calculate theta after a time of 0.2 seconds. We can use the relationship between angular velocity, displacement, and time, since the angular velocity is constant. The formula is theta equals omega times t. Let's substitute the values we know. We found omega to be 75.408, and the time t is 0.2 seconds. Multiplying these together gives us a result of 15.0816 radians. This is the total angle the flywheel turned in that 0.2 second interval. So we've successfully calculated both the angular velocity and the angular displacement. That's our first problem solved. Let's compare our answers to the memo to ensure accuracy. Now let's compare our solution for question 1 to the provided memo. We need to be careful with the value of pi. First, for part A, the angular velocity. Our calculation, using pi equals 3.42, resulted in 5.408 radians per second. The memo, however, seems to have left its answer in terms of pi, 24 pi radians per second. If we calculate this, 24 times 3.142 is 75.408 radians per second. So, our answers are numerically identical. The memo just presented it differently. Now for part B, the angular displacement. Our answer was 15.816 radians. The memo's answer is 4.8 pi radians. If we multiply 4.8 by 3.142, we get 15.0816. Again, the answers are numerically the same. The memo's solutions are correct, but they maintain the pi symbol for simplicity. Our approach of substituting pi early was also correct because we used the specified value. You will get the same final answer. Let's move on to Activity 2.1, Question 2. The question states, the rotational frequency of an axle accelerates uniformly from 10 revolutions per minute to 600 revolutions per minute for 4 seconds. Calculate A, the angular acceleration, B, the average angular velocity, C, the angular displacement after 4 seconds, and D, the number of revolutions after 4 seconds. This problem involves acceleration, which means the velocity is changing. The most important step here is to ensure all our units are consistent. The frequencies are given in Rmin, but the time is in seconds. We must convert the frequencies to revolutions per second. The initial frequency, N1, is 10 revolutions per minute. To convert to seconds, we divide by 60, giving us approximately 0.1667 revolutions per second. Similarly, the final frequency, N2, is 600 revolutions per minute. Dividing by 60 gives us exactly 10 revolutions per second. The time duration, T, is 4 seconds. Now all our units for N and T are consistent. This conversion is a critical step to get the correct answer. Let's solve part A, the angular acceleration. We need to find x. To find angular acceleration, we can use a formula that relates acceleration, frequency, and time. The formula is x equals 2 pi times the quantity n2 minus n1, all divided by time t. Let's substitute our converted values in pi. Plugging in the numbers, we have 2 times 3.142 times the quantity 10 minus 0.16667, all over 4. First, calculate the term in the parentheses. That's 9.83. Now multiply the numerator. 2 times pi times 9.8333 is approximately 61,785. Finally, dividing by 4 gives us an angular acceleration of 15.446 radians per second squared. This tells us how rapidly the axle's rotation is speeding up. Now for part B, the average angular velocity. We need to calculate omega average. First, we need the initial and final angular velocities, omega 1 and omega 2. We use the formula omega equals 2 pi n. Omega 1 is 2 times pi times 0.1667, which is 1.047 radians per second. And omega 2 is 2 times pi times 10, which is 62,084 radians per second. Now we use the formula for average angular velocity, which is the sum of omega 1 and omega 2 divided by 2. Plugging in our values, we get omega average equals 31.944 radians per second. This represents the constant angular velocity that would result in the same displacement over the same time. Let's continue with part C, angular displacement. We need to find theta. We can use the formula connecting average angular velocity, time, and displacement. The formula is theta equals average angular velocity times time t. We found omega average to be 31.944 and t is 4. Multiplying them, we get a total angular displacement of 127.776 radians. This is the total angle the axle rotated through. Finally, for part D, the number of revolutions. We need to find n. We have the total angular displacement in radians, so we can use the conversion factor. 1 complete revolution is equal to 2 pi radians. Therefore, to convert radians to revolutions, we divide by 2 pi. Plugging in our value for theta, we have a 127.776 divided by 2 pi. This gives us approximately 20.33 revolutions. Alternatively, we can use the average rotational frequency. The average rotational frequency, N average, is N1 plus N2 divided by 2. This comes out to be 5.083 revolutions per second. Then, to find the total number of revolutions, we multiply this average rate by the time of 4 seconds, which again gives us approximately 20.3 revolutions. Both methods confirm our answer. That was a detailed problem with multiple parts. We've found the angular acceleration, average angular velocity, angular displacement, and the total number of revolutions. The key was careful unit conversion. Now let's compare our solution for question 2 with the memo's solution. We'll go through each part. For part A, the angular acceleration, our answer was about 15.446 radians per second squared. The memo's answer is 4.9117 pi. If we calculate 4.917 times 3.142, we get 15.446. The answers are the same. For part B, the average angular velocity, we calculated approximately 31.9444 radians per second. The memo's answer is 36.927. There's a difference here. Let's look closer. The memo made a slight rounding error in calculating omega 1 and omega 2. It rounded 0.667 to 0.083 for omega 1. However, our method of calculating the average frequency and then converting that to average angular velocity is more precise and leads to the correct value of 31.944 radians. For part C, the angular displacement, our answer is 127.76 radians. The memo has 221,562. This difference is a direct result of the error in part B, as the memo used its incorrect average angular velocity. For part D, the number of revolutions, we found approximately 2033 revolutions. The memo has 35.25. Again, this error propagates from the earlier incorrect calculations. Our answer of 2033 revolutions is correct based on the initial data. So for question 2, our method and answers for parts B, C, and D are the more accurate ones. Part A is correct in both cases. This shows the importance of careful calculation and unit conversion. We're now on our final question, question 3. The question is, the spin dryer of a washing machine accelerates uniformly from 5 revolutions per minute to 700 revolutions per minute for 6 seconds. Calculate A, the angular acceleration, B, the average angular velocity, C, the angular displacement after 6 seconds, and D, the number of revolutions. This problem is very similar in structure to question 2, which means our strategy will be the same. First, convert to consistent units. We must convert the rotational frequencies from revolutions per minute to revolutions per second. The initial frequency, N1, is 5 revolutions. Dividing by 60 gives us approximately 0.083 revolutions per second. The final frequency, N2, is 700 revolutions. Dividing by 60 gives us approximately 11,667 revolutions per second. The time duration T is 6 seconds. Our units are now ready. Let's begin with part A, the angular acceleration. We need to find x. We'll use the same formula as before. X equals 2 pi times the quantity n2 minus n1, all divided by t. Substitute our values. This becomes 2 times pi times the quantity 11.67 minus 0.083, all over 6. Calculate the difference in the parentheses first. That gives us 11.5. Now multiply 2 times pi times 11,584, and then divide by 6. This gives us approximately 12.133 radians per second squared. This is the constant rate at which the spin dryer's angular velocity increases. Next, part B, the average angular velocity. We need to find omega average. Again, we'll first find the initial and final angular velocities, omega 1 and omega 2. Omega 1 is 2 pi times n1. That's 2 times pi times 0.083, which is 0.521 radians per second. Omega 2 is 2 pi times n2. That's 2 times pi times 11.667, which is 73.32 radians per second. Now we can calculate the average angular velocity. Omega average equals omega 1 plus omega 2 divided by 2. Plugging in our values, we get an average angular velocity of approximately 36.927 radians per second. This is the constant angular velocity that would produce the same angular displacement. Let's move to part C, the angular displacement. We need to find theta. We use the formula connecting average angular velocity and time. Theta equals average angular velocity times time t. Multiplying our average angular velocity, 36.927, by the time 6 seconds, we get approximately 221.562 radians. This is the total angle the spin dryer rotated during the acceleration period. Finally, part D, the number of revolutions. We need to find an. Similar to question 2, we'll convert our total angular displacement from radians to revolutions. Number of revolutions equals theta divided by 2 pi. Dividing 221,562 by 2p gives us approximately 35.26 revolutions. The spin dryer completed about 35¼ turns during those 6 seconds. And that concludes the calculation for question 3. We've found the angular acceleration, average angular velocity, angular displacement, and the total revolutions. Let's compare our solution for question 3 with the memo's solution. We'll check each part one by one. For part A, the angular acceleration, we calculated approximately 12.133 radians per second squared. The memo's answer is 12.132, which is essentially the same, just a slight difference in rounding. For part B, the average angular velocity, we calculated approximately 36.927 radians per second. The memo has 36.927 as well. This time our answers match perfectly. For part C, the angular displacement, we calculated approximately 221,562 radians. The memo's answer is 221.562, another perfect match. For part D, the number of revolutions, we calculated approximately 35.26 revolutions. The memo has 35.25. Again, this is a very close match, likely due to small rounding differences. So for question 3, our results are in excellent agreement with the provided memo. This confirms our understanding and application of the formulas. Let's quickly recap what we've accomplished in this tutorial. We started by outlining the key formulas for circular motion: angular velocity, acceleration, displacement, and the number of revolutions. Understanding these relationships is fundamental. We then walked through 3 example problems step by step. In each case, we first extracted the given information, being very careful with units, and then systematically applied the correct formulas. We calculated everything from acceleration to total revolutions. One of the most important takeaways from today is the need for consistent units. Always ensure your frequencies are in revolutions per second or radians per second when your time is in seconds. This step is critical for getting the right answer. Thank you for joining this tutorial. We hope you now have a clearer understanding of circular motion. Please subscribe for more tutorials from Math Zone African Motives to help you master your math and science subjects.